So today we'll be going over homework number 2, problem 25.44, where the problem states that charge Q2 in figure 25.44 is in static equilibrium, and it is asking to find the charge for Q1. So for figure 25.44 shown here, we have a point charge of Q1, which is 10 centimeters away from Q3. Q3 is a positive charge of 5.0 nanocoulombs, which is 10 centimeters away from Q2 charge. And so when the question states that Q2 is in static equilibrium, we know that the net electric field acted on the Q2 point is in fact 0. So we can have an equation of the electric field net at Q2, which is equal to the electric field of all charges acting upon Q2, which is the electric field of Q1 plus the electric field of Q3. So the sum of that will be 0. And from our knowledge in physics 6C, we have our equations of electric field, which can be rewritten as the E net of Q2 is equal to the K constant times the absolute value of Q1 charge divided by R squared of Q1 to Q2 plus the K constant times the absolute value of Q3 over R squared from Q3 to Q2, which is equal to 0. And an important point about this is, since we don't know yet too much about the charge of Q1 in terms of the direction, we have to put a plus or minus I hat in order to indicate that we don't know the direction, the charge, whether it's a plus or minus Q1 charge. But we do know that Q3 is a positive charge in our conventional direction. We know that the electric field from +1 will move away from the source and outwards, so we'll have a positive I hat direction. But since we know that the E net of Q2 has to be 0, we know that the electric field of Q3 has to be equal in terms of magnitude of the electric field of Q1, but an opposite sign, because we can rewrite this as E Q1 is equal to negative EQ3. So since we know that EQ3 has a positive direction, we have to conclude that Q1 will have a negative I hat direction plus K value Q3 R squared positive I hat is equal to 0. And so now we have our equation. Now we need to plug in what we know and figure out what we don't know. So we know that Q3 is equal to positive 5 nanocoulombs, which can be rewritten as 5 times 10 to the negative 9 coulombs. In terms of conversion, we know that from Q1 to Q2 we have an R distance of 20 centimeters, which can be rewritten as 0.2 meters, and from Q3, R is from Q3 to Q2, which is 10 centimeters, which can be rewritten as 0.1 meters. And K is our constant of 9 times 10 to the 9th newtons meters squared over coulombs squared. And so now we can plug in our knowns, and we don't know Q1, which is what we're looking for. And so we can plug in 9 times 10 to the 9th newtons meters squared coulombs squared times the absolute value of Q1 over R squared in terms of Q1 to Q2, which is 0.2 meters squared with a negative I hat direction, plus 9 times 10 to the 9th newtons meters squared per coulomb squared times Q3, the absolute value of 5 times 10 to the negative 9 coulombs over R squared of Q3 to Q2, which is 0.1 meters squared, is equal to 0. And so if we do simplify this out, we get 2.25 times 10 to the 11th newtons per coulomb squared with a negative I hat times Q1 is equal to 4.5 times 10 to the 3 and then positive I hats. And so this will be in terms of newtons per coulombs. And so when we solve for Q1, we divide both sides by the 2.25 times 10 to the 11th newtons per coulomb squared divided by 2.25 times 10 to the 11th newtons per coulomb squared. And so this gets canceled out, and then our units on this side will be left with coulombs on top since it's a fraction beneath a fraction. And so we will get the absolute value of Q1 is equal to 2.0 times 10 to the negative 8 coulombs. But also we can't forget about the negative I hat direction. And so when we don't have the absolute value, we know that Q1 does in fact have to be a negative charge because of the negative I hat. And so we can rewrite this in terms of also nanocoulombs. So 20 nanocoulombs will be our Q1 charge. And this will be our final answer. And this concludes homework number 2, problem 25.44. Thank you.